last time we started into chapter 3, which is sequential logic. I mentioned in class that, and also it was on the exam, the difference between combinational and sequential logic is that sequential logic has memory. However, it also has in order to have memory, it also has to have a clock. So when you guys took 211, you learned combinational logic mostly. And as I understand it, you didn't really get into sequential logic in that class. So you might have been wondering, after having taken 211, where the clock comes into play. Because when you go buy a computer, there's references to clock speed, right? And also, when you took 212, you talked about the clock in terms of microarchitecture. So when we started this chapter out, we took a look at how you design latches, like the SR latch. And this component does not have a clock, but it allows you to store a value internally inside this thing. It allows you to keep a bit of memory in this component, which is output as Q, and then you can reset it to 0 by setting R and S to 0, 1. You can set it to 1 by setting, I'm sorry, I screwed that up. R and S, if reset is 1 and set is 0, you capture a 1 inside of that latch, or you set it to be, you set it to 0. I screwed that up again. If reset is 1 and set is 0, then you'll put a 0 in there inside that memory cell. And then if you have reset as 0 and set as 1, then you'll put a 1 in there. And then the reason for that is because then if you set both of those inputs to 0, then the previous value written into there, a 0 or 1, will continue to be output, right? So that's your memory behavior. Now those are tough to work with. So a RS latch can have some extra logic bolted onto the front of it to create a D latch, which introduces a clock input and a D input. The clock, when the clock is 1, it will take D, and D will go through these gates, and it will, if D is 0, R will be 1 and S will be 0, right? And if D is 1, it'll flip them, right? So in other words, what is the point of this? Well, the point is it makes it a little easier to use, because now you have one signal that's used as kind of the doorway that you can open and close to let this other signal D in. So in other words, when clock is 1, it's like the door is open and D will enter this memory. And then when clock is 0, you close the door and you trap the previous value of D inside there. Does that make sense? Okay, so that is a level, that would be a level sensitive behavior where the behavior is determined by the level of clock. And then we talked about a further improvement where if you take two D latches and connect them together this way, you can create a flip-flop, which is where it exhibits an edge-sensitive behavior, where it's the clock edge that takes the value of D and accepts it into the memory and stores it in there. So the advantage there is that the time it takes for the clock to go from 0 to 1, if this is a rising edge triggered flip-flop, is a very small amount of time, and it allows you to instantaneously capture the value of D. Okay, so the circuit becomes very stable, because the time in which you're accepting new values is a very short amount of time. It's like taking a snapshot, where the clock edge represents sort of taking a snapshot where the shutter opens and closes very fast, right? Only according to the time it takes the clock to rise. You guys with me on that? Kind of find this a little difficult to explain, but that's Now, most sequential logic circuits use this edge-triggered flip-flop. So just a point of terminology, if you see latch, that latch refers to a level-sensitive device, and a flip-flop is a edge-triggered component device, right? Primitive, whatever you want to call it, cell. Everyone with me? Now, why am I emphasizing this? Because those terms are a little confusing. Like, why does latch mean level sensitive and flip-flop mean edge sensitive? It's kind of a the terminology is confusing. I always thought it was confusing anyway. Okay. Now, there's a couple other features you can add to a flip-flop. You can add an enable, which allows you to tell the flip-flop to ignore the clock for a while. So you can disable the flip-flop and you can make it hold values across multiple clock cycles with enable. That's pretty common. You don't always see enables, and they're not always used. If you see a flip-flop symbol, like this is actually a register symbol. This is a flip-flop, but it has 4 bits. It's like having 4 flip-flops in parallel. But notice that there's a clock input. There's no enable. There's no reset. There's no set. And so it's implied that if there's no enable input, that it is always enabled, meaning that this thing can potentially change on every cycle, right? Unless, of course, the input doesn't change, in which case the output won't change, right? But this, generally speaking, when the input is changing, you'll see this Q change on every cycle. You guys with me? Okay. But on the other hand, if you have this enable input on here, then that implies that there's another input on this thing that allows the whatever circuit that this component is instantiated into can control it and can disable it for a while, right? Okay, so an example, by the way, I was trying to think of examples last lecture. You could think of this like another example is if you have a processor that has to stall, right? So processors generally try to continuously execute instructions from a program. But sometimes if you have a cache miss or you've got some, you have some structural hazard, sometimes you have to stall. You have to tell the processor to stop, to freeze for a while. And so if the program counter, which controls where in the program the processor is executing, if it has an enable on it, then by setting that enable to 0, you're stopping the processor in its tracks. You're preventing the program counter from advancing, and thus you're preventing the processor from advancing in the instruction stream in the program. Okay? So that would be a use case for an enable. There's also a reset input sometimes you see on flip-flops or registers. And the reset is, that's actually pretty common. And usually there's a reset whether you see it or not. A lot of times it's just assumed that all your flip-flops and registers are connected to a global reset. And the reset allows you to just, generally that's a way to initialize all your registers to 0. It gives you a sanity state. They used to call that a sanity state when I was in school. I think that term is a little out of date now. But it gets you back to a known state. For example, when you power up a system, there's generally a reset that happens at the beginning. You pulse a reset. Everyone with me? Okay, and then there's also a set input. I think they show set. Yeah, sometimes you'll see a set. This is a little rare. It's just like a reset, but it sets it to 1 instead of 0. Okay. The book takes a little detour here. It talks about a ring oscillator circuit. These are neat, but they're not really all that practical, and they're difficult to analyze. So we'll just kind of skip over that. I talked about that a little bit last time. Okay, so the important part of this lecture is how to design sequential logic circuits. You guys know how to design combinational logic circuits now. We looked at doing them, designing circuits with Boolean logic and applying theorems to transform one form of a Boolean expression into another, to minimize it or to change it in other ways. We, have canonical form and non-canonical forms. We looked at using K-maps, Carnot maps to minimize combinational logic, and of course we looked at truth tables. So how do you design sequential logic then? Well, this is quite a bit more complicated. So first of all, when do you use sequential logic? That's the first question. Sequential logic is used whenever you need to take a combinational logic circuit and break it up into multiple clock cycles. So this is something actually you probably talked about a little bit in 212, but in the last chapter we talked about propagation delay. So depending on what a combinational logic circuit is doing, it could have a very long propagation delay. And in a CPU, your clock speed is going to be limited by the longest possible delay, your critical path. So you can use sequential logic to break up long logic paths and spread out the combinational logic workload across multiple cycles by storing intermediate results into a register or a flip-flop. Does that make sense? So you guys talked about this a little bit in 212. This is basically pipelining, is what I'm talking about. There's also this idea of reusing logic. So sometimes, like for example, if you're building a circuit like let's say a divider circuit. Divider circuits have to do repeated subtraction and shift operations, right? You guys remember that you should have talked about that a little bit in 212. So in order to build a divider, you have to keep trying to subtract the shifted version of your divisor into your dividend. So you have a divisor, you have a dividend, and the divisor, you keep trying to subtract it from the dividend, shifted versions of the divisor, right? The problem is that you may only want to have one subtraction circuit, one functional unit. And so in order to reuse the same piece of hardware for multiple operations, you can split up the whole thing into clock cycles, which allows you to store intermediate differences in a register, and then you can keep feeding that register back into a subtractor. You guys with me? I know it's kind of esoteric. But the idea basically is that sometimes you want to reuse the same hardware. You want to take the output of some logic and feed it back as an input. And with normal combinational logic, you can't do that. It's against the rules. You don't want to have any cycles in your combinational logic circuit. But by inserting registers in that cycle, you break up the cycle. You guys with me? So like if you have, like for example, a multiplier circuit. A multiplier is built by doing a whole bunch of adds, where you're shifting the multiplicand, right? And so you can reuse that adder by feeding the output of the adder back into itself again, but inserting a register in there and it breaks it up. So it can that turns into not a pipeline circuit, but a multi-cycle circuit, right? It's not pipeline because you can only do one thing at a time, but it's spread out over multiple clock cycles. You guys with me? Okay, so that's one of the reasons you want to use it. Sometimes you build sequential logic for things that you want to use for sequencing operations. Like you want to be able to have different things happen in different cycles. For example, and there's an example I might show a little later where, like if you build a controller for something like, say, a soda machine, right? Where you want to be able to, put money in and have it keep track of how much you've put in, and then once you've put in enough, it can either release the soda, or it can release the soda and also some change, right? But it can only release one coin per cycle, so there's these sequences of events that have to happen. And sequential logic is useful for things like that. Okay, so there's some rules. The book has these rules of synchronous sequential logic composition. In a synchronous logic circuit, every circuit element is either a register or a combinational circuit. Well, that's pretty obvious because what else could be in there? I I guess the idea is that you don't want to, you're going to have classical combinational logic and these registers or flip-flops, right? At least one circuit element is a register. And by the way, please don't get confused. Register and flip-flop I'll use interchangeably in this lecture. I do that all the time. Register and flip-flop, just to be clear, it's the same thing. The only difference is a register is a multi-bit flip-flop. Instead of storing one bit, you're storing multiple bits, right? So that's kind of weird too. So don't let that confuse you. All registers receive the same clock signal, so that's pretty typical. A lot of times too, even though we're showing a clock, you see there's a clock input on this guy. It is very common that you won't even show the clock. You'll just show little rectangles that represent registers or flip-flops, and you won't even bother to show the clock because it's assumed that you have a clock connecting, you have a global clock that connects everything, right? As well as a global reset, as I mentioned earlier too, okay? Every cyclic path contains at least one register, and that's because, again, you don't want to have cycles in purely combinational logic. So I also mentioned, I mentioned pipelines. So there's these finite state machines, which is a way to design simple sequential logic circuits, generally for sequencing operations, like when you want to design a controller for something. For example, if you design a cache for a processor, there has to be sequencing in there, because if you get a cache miss, you have to be able to go to the memory, request memory access. You have to wait for the latency of the memory, and then you have to request each of the words that go into a cache line. So there's this word 0, word 1, word 2, word 3, go back, right? So there's this sequencing that happens. Also, as I mentioned, these multi-cycle circuits. Like if you say, a lot of CPUs will have a divider, or some CPUs will have a multiplier or a floating point unit that require multiple cycles to do their work, to produce their result. And so in that case, you need a finite state machine in there to control the routing of data and the operation of the circuit across multiple clock cycles to have it work, right? So that's a finite state machine. So how do you design a finite state machine? We're going to start with that. So an FSM consists of 3 parts. And when you design, it's very common that when you design circuits, even in hardware description language, HDLs like VHDL and Verilog, it's very common that you'll design finite state machines in there. And when you do, you still have 3 pieces of your code that make up the 3 main parts. There's the flip-flops or the registers themselves that hold the current state value. That is what basically, I like to think of it like, what is the circuit doing right now? What's its state? And that's basically just a register. It's in VHDL or Verilog, you would call that clocked. That's your clocked process or your clocked block. It just basically takes the next state value that's coming in as an input, and on the clock edge, it will trap it into the current state. So the next state will become the current state on every clock cycle, every clock edge, usually rising edge. You could be falling edge, but it's either the rising or falling edge of the clock. Everyone with me? So that's pretty simple. That's pretty much just a register. Then you have next state logic, which is purely combinational logic. It's a combinational logic circuit that generates the next state value from the current state value and the inputs, right? So you design a combinational logic circuit using Boolean logic or K-maps or Quine-McCluskey or however you want to do it, but you're creating this for the purpose of computing the next state from the current state and the inputs. Everyone with me? Think of it as the next state table. And then you've got output logic, which is also purely combinational logic. And that generates the outputs of the state machine as a Boolean function of the current state, right? And optionally, the inputs. But that depends on what style of state machine you want to create. There's two styles, Mealy and Moore, and I'll get into that for a minute. So, in a minute. So, three components. There is the register, or the flip-flops, right? This is the state register. I think it's state register that has the clock and usually a reset in there as well. And that's it. It's just the memory part. Then there's the next state logic, which is combinational logic, and the output logic, which is also combinational logic. Okay? So there's no clock involved in the next state logic or the output logic. Okay, so I mentioned that there's two styles of finite state machines. There is what they called there's a Moore and a Mealy. I don't know exactly what the history of those looks like. I mean, they're obviously someone's last name. But there are Moore machines and Mealy machines. The only difference is that a Moore machine has outputs that are only functions of the current state. And a Mealy machine has outputs that are a function of the current state and the input. Now you might be thinking, well, who cares? What difference does that make? The difference is that with a Moore machine, the outputs only change on the clock edge. They can only change on the clock edge, I should say. They don't always change. But the only time the outputs of a Moore machine can change are on the clock edge, which means that a Moore machine is synchronous. Everything is synchronous. A Mealy machine, on the other hand, its outputs are asynchronous in the sense that basically I have essentially a different. You could think of it as having a different combinational logic circuit for every state. So once you get into a state, you're going to stay in that state for at least a cycle. But during that cycle, if you change inputs, you could potentially be changing the outputs as well. So the outputs don't necessarily just change on the clock edge. You guys with me? Now you might say, again, all right, well that's very subtle. That's right, well who cares? Well, the way that you design Mealy and Moore machines are different. And I'll get into that in a minute. But the way you can remember this is the way I always remember this is more is less. Because a Moore machine is simpler in the sense that the output logic is simpler. The output logic doesn't have to worry about the inputs. It only worries about the current state. So in that sense, Moore is less because Moore has less functionality than a Mealy machine. In fact, you can make a Mealy machine as a Moore machine if you just make the inputs don't cares in the output logic. So in that sense, a Mealy machine is a superset of a Moore machine. A Mealy machine, the class of Mealy machines includes the Moore machines, right? So Moore machines are more restrictive. They're more restrictive, so that's why you can think of it as more is less. Okay? This is a picture of that. So this is a Moore machine where the output logic just looks at the state and generates the outputs. And in a Mealy machine, the output logic looks at the state here and the inputs as well that come around and plug into the output logic. You guys with me? Now in both cases, the state feeds back into the next state logic, right? Because the next state is always a function of the current state and the inputs. That way the inputs can control the sequence of states that you go through. Okay? Okay, so let's look at an example. This is a traffic light controller, very simple one. The idea is you have an intersection and there are two lights. There's light A, which controls the horizontal traffic here, east-west traffic. And then there's light B that controls the north-south traffic, right? Light A and light B are two inputs each, correct? Yeah. So light A and light B can be red, green, or blue. So they're encoded values. Not red, green, red, yellow, and green. Sorry, I was thinking red, green, and blue. Red, yellow, and green. Okay, let me turn that. Red, yellow, and green. Right, everyone with me? All right, so the way this thing works is that obviously you can only have, if one of the lights, only one of the lights can be green at a time. And the controller will not change the state of either light until it detects that there's no traffic on that street anymore. So as soon as, for example, if the traffic light A is green, B will be red, and as long as there's traffic flowing on this east-west road, it's going to stay in that state until there's no more traffic. So there's a traffic sensor, which is, well, there's two traffic sensors. One for this A, which is east-west, B is north-south. Everyone with me? Does that make sense? Okay, so the traffic sensor is Boolean, true when it detects traffic, and then the lights could be red, yellow, or green. All right, so the traffic light controller, if we look at it from a module level view, top level view, we've got, it's going to have a clock and a reset, which are both inputs. Then it's got the single bit traffic A and traffic B inputs coming in, which are, just the binary traffic detectors. And then there's light A and light B outputs. And notice that these guys have the little lines here that indicate that they're more than one bit. They're a multi-bit signal. Okay. So when you design a finite state machine, you design it as a graph. It's comprised of vertices, nodes, circles, and arcs, or edges, or transitions, which are lines that connect the circles together. Each circle represents a state, and the arcs represent transitions from one state to the next. In most cases, you can't get from any state to any other state. There's restrictions, and so you can tell that from looking at which edges you have connected to each pair of states, right? That represents all the valid transitions from one state to the next. So now in this case, we'll start off with this this first state, and notice that there's this thing that says reset. It points to it. That's the thing I was referring to earlier that they used to call a sanity state. It's the state that you go to automatically if the reset input is asserted. Now, last time I talked about, resets can be synchronous or asynchronous, depending on whether we want to wait for the clock edge to actually initiate the reset. In this case, it's not specified, right? We're just that's kind of an implementation detail that's not shown in a state machine diagram. So in the reset state, in the default state, the initial state, light A is green and light B is red, meaning that when we start the system up, the east-west traffic can flow and the north-south can't, right? We'll also label that state S0, which we're just going to, I don't know why it's S0, that's just the name we're going to give it. Okay, so there's 4 total states because whenever we transition from red to green, we need to go through the yellow phase where the light that's about to transition from green to red is yellow for a while. So in S0, light A is green, light B is red. And in state 1, light A is yellow and light B stays red. And we're going to trigger that transition whenever there is no traffic on A. So you see there's T, A, bar, right? Now this is a little can be a little confusing because the notation is kind of abbreviated. What they really mean here is TA has to be 0. But what about TB? Do we care what that is? No, it's a don't care. So it's just not shown. It's kind of a shorthand, right? If TA is 1, or is as long as TA is 1, meaning that there's east-west traffic, and we're in the state where our east-west light is green, then we're going to stay there. So you have this loop back. You see that? So as long as TA is true, we're going to stay in S0 if we're in S0. But whenever TA is false, we're going to transition to this intermediate state where we turn the east-west light yellow, and then we will go unconditionally to state S2 where we're going to have the east-west light is red and the north-south light will be green. And we will stay in that state as long as we have traffic on the north-south road. Everyone with me? Now, what's up with this unconditional transition? How long is it going to take for us to take that? Well, there's an assumption here that the clock signal that controls this is running pretty slow. The clock, in order for this to work, the clock would have to have a period that equals the amount of time we want the yellow light to be on, right? So this thing is essentially running on a clock as it's written here. That's, I don't know, 10 seconds, 10-second period, right? You guys with me? Meaning that every 10 seconds, not only would you stay in this yellow light state for 10 seconds, but you would also only be checking for traffic every 10 seconds as well, right? So in other words, you might not have traffic, but as long as you get traffic with it before that 10-second clock period is over, the state machine won't notice it because it only actually checks. These transitions are only checked on the clock edge every clock cycle. These transitions are checked every, in this, like for example, every rising edge of the clock. Everyone with me? Okay, so you get down here, and you've got the east-west road is red, north-south road is green, and you stay in there until you have no traffic on the north-south road, in which case you transition that one to yellow. You stay in there for one cycle, and then you come back to the original state. Yes?
So if there was a car going through at like every single clock cycle, it was just like going across, like every single clock cycle, there's a car.
It would never change. Yeah, that's right. Yeah, this doesn't have a timeout. Now we could introduce that, by the way, pretty easily. We could have a counter or something that gets reset. We could have a counter that this machine can reset whenever it goes into the yellow state because it's only there for one cycle, for instance. And then we could have another input that checks to see when that counter exceeds a certain value. That'll be our timeout, in which case then we can switch to the yellow state regardless of whether there's traffic or not. So that's something we could add to this, right, if we wanted to, but this doesn't include that. One of the problems, by the way, the reason it doesn't include that is because, and I'll show you in a minute here, but these things get really complicated really fast. It becomes impractical to design these on paper whenever you introduce too many inputs. Because remember that just to add some context here. Remember the K-map, right? The K-map only scales up to what, six inputs. Generally, I think in our book, they only went up to 4 inputs, right? You could go up to 6 inputs, but beyond that, you can't even solve it anymore because it would require four-dimensional picture, right? K-map. At least I've never been able to. I've never seen any way to do a K-map with more than 6. Maybe there's a way to do it. Maybe there's a trick to do it. But anyway, my point is that remember that the next state logic is a function of the current state and the input. So whenever you build your k-maps, for example, for the next state function, you have to include all the inputs and all of the bits that represent the state, right? So it gets big really fast. Now, if you're writing in an HDL, then the tools take care of that for you. So you can build much bigger state machines if you have the benefit of a hardware description language, which we'll get into in the next chapter. Okay, so if I want to build this thing, you have, let me write this up here. So you have current state. Now, what is this, by the way? This is the next state table that I'm constructing. So we have current state, inputs, and next state. Now, as I mentioned, the next state table is purely combinational. What is it? TA, TB, right? Purely combinational. So this is just a truth table. There's no clock or anything like that in here. We just want to create essentially the inputs. This next state output from this table is going to be connected to the D inputs on the registers. Remember, the registers have D as the inputs, Q as the output. So these things are going to go into the D inputs, and the current state is the Q outputs. You guys with me? Okay. Okay, so if my current state is S0, and I remember the reason I wanted to do this is so I can show the state machine here. Right. So if I'm in S0, and let's see, if TA is 1, right, I want to stay in S0. So my next state will also be S0, right? But TB is a don't care. So this row, because I've got a don't care as my input, this row is actually a shorthand for having two rows where I have both possible values of TB in there, right? You guys with me? This is an abbreviated, collapsed form of two separate rows that would account for both values of TB. If I'm in S0 and I have no traffic on TA, and again, TB would be a don't care, then I want to go to S1. So this row represents my loopback transition, and this row represents my transition from S0 to S1, right? Notice there's no way for me to get I can't go from S0 to S2 or S3. That's illegal, right? The state machine won't do that. If I'm in S1, then both my inputs are don't care, and I'm going to go to S2, right? So this transition, this row represents the transition down from S1 to S2. Now, you might say, wait a second, like why? I mean, why does it take a clock cycle to do that? Only because each row of this table, in order for the next state to take effect, to become the current state, it takes a cycle, right? So, if you look at the design for this, it's a loopback, right? So what this really is this is logic that has a cycle, which in pure combinational logic you wouldn't want to do that, but in sequential logic you're putting the state register there, breaks up that cycle. Okay, so we'll go back here to this. Okay, right. So then if I am in S2, that represents the green light on the north-south road. So I am going to wait for there to be no traffic. As long as there is traffic, then I'm going to stay in S2. And if I'm in S2 and I have no traffic, then I'm going to go to S3. And if I'm in S3, I don't care what happens here. I'm just going to go back to S0. Make sense? Okay, so, but the problem is, how do you design the logic for this when I'm using symbolic names for the states? Well, you have to, after you design your state machine, you need to go back and set values, Boolean values, or essentially binary values for each state. So first question you have to ask is, well, how many bits do I need? Well, there's 4 states, so I take the log base 2 of 4. That means I only need 2 bits to represent my state. So notice that my state is S sub 1 and S sub 2, which represents the 2 bits of my state, right? Then the next question is, okay, how do I assign values to each of the states? However you want. Doesn't really matter, because once you assign the values, then you'll design the next state logic that'll lock in whatever values you chose, right? Well, when I say we've already designed the next state function, but you'll design the actual hardware for it, right? You guys with me? So S0 is here's they have the secondary. The S0 is 0, 0, and that's the only one that has to be. That's the one that actually. That's the only one that's not arbitrary, because we said that S0 is our reset state. And so the reset state, in order to guarantee that we'll go to the reset state on a reset, that state value should be 0, 0, because when you set your global reset signal, it will set the state register to zeros, right? All right, so that one we want to be 0, 0. But the other ones, yeah, it's whatever you want, however you want to assign them. So in this case, we've got state 1 is 0, 1, state 2 is 1, 0, and state 3 is 1, 1, which makes sense, right? Because that's just a binary version of the numbers there. Okay, so once you've got that, you can fill in, you can replace the current state here with the actual state encoded, the encodings. Right, and at that point you can kind of you can disregard the symbolic names there. So state 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0. And now we've got a truth table. We've got a truth table we can actually synthesize into logic. We can build a circuit for that, right? Now you might say, wait a second, hold up. Truth table, how do you generate 2 outputs from a truth table? You would have to you can have multiple outputs, but remember, when you design the logic, when you synthesize the hardware, you're going to have a separate circuit that generates each bit of the next state value. You guys with me? So the book says that the notation here, by the way, is S prime sub 1 is bit 1 of the next state value. And this is kind of interesting, because the next state is just S1 XOR S0. Right? Does that make sense? I say that because the inputs aren't part of that expression, right? Well, yeah, because see, state 3, how does that work out? Yeah, so state 1 and state 3 have unconditional transitions coming out of them. And the way we encoded that is 0, 1, and 1, or 1, 1. Sorry, 0, 1. So state 1 is 0, 1, and state 2 is 1, 0, right? So let's see. So if we've got, I don't have a version of this here. Let me put that. So over here. So this guy's got a loop back. This guy's got a loop back. 0, 0, 0, 1, 1, 0, 1, 1, right? So state 3, which is the lower, yeah, the lower left-hand corner one, right? All right, so the next state function for S1 prime is just S1 XOR S2, right? So S1 prime is going to be 1 when we go from here to here, right? So when we're in this state, S1, the XOR is going to give me a 1 regardless of the input. So that makes sense, right? I'm going to transition here unconditionally. When I'm in this state, I've got a loopback, an unconditional loop, not an unconditional loopback, but well, no, sorry. I'm either going to loop back or I'm going to come to this state, but in either case, my S1 will be 1, right? So it doesn't matter what my inputs are, because if I am in this state, S2, then I know my next state will have a 1 in its most significant bit location, because I'm either going to stay here or I'm going to go here. Either way, there's a 1 there. So that makes sense, right? If I'm in 1, 1, well, 1 XOR 1 is 0. Well, that makes sense, because I'm going to go there unconditionally, right? That makes sense. And if I'm in this state, 0 XOR 0 is also 0, which is the same whether I stay in that state or I go to this state. So that makes sense, right? That seems to follow. Of course, I could have just solved the truth table and arrived at that as well. S sub 0 prime is a little bit more complicated, and it does include the inputs TA and TB. So for that, you can look at, let's see, S0. So we've got 1, 2, 3 minterms there, right? Well, actually, I've got a don't care, so there's more than that. But in this case, if you take this one, there's S1, not S1, not S1, S1. Sorry, not S1, S0, right? Let's see. Let me write that out. So we're looking for. We're trying to calculate this one, this guy, and this guy, right? So, right, and so S1, did I mess that up? S1, so current state 0, 1, right? Right, yeah, that's true. Yeah, so if you've got a 0, 1, then my S1 prime is going to be S1, not S1, right? Right here, right? And S0, right? And I don't care what my inputs are. Does that make sense? Yeah. Or, let's see, what's my other case here? I've got 2 more. So I've got S1 and not S0, right? And if that is true, then TA, I don't care what TA is, and well, look at that, I don't care what TB is either, right? Because TB is a 0 and a 1, right? Guys with me? So that's going to be S1 and not S0. Yeah. Yeah, so is that, let's see, do they have a redundancy in here? S1. So they're saying not S1, not S0, which would cover, that would cover these two, right? Oh, sorry, that's S0. Yeah, sorry. I lost, I know, I see where I screwed up. Yeah, we're looking at S0 prime. We already did S1. Yeah, so we already figured that one out. And that was just, that. By the way, what I had there that just collapses, that is equivalent to the XOR gate. S0, right, sorry, here we go. So that would be these two guys, right?
Yeah.
So that's S, not S1, not S2, not S0, right? So those are both 0. And TA, not, right? And then this row is S1, not S0, and not TB. There we go. And yeah, that's what they've got. Matches up. Okay, any questions about that? Okay, well that just gives us the next state logic. Now we have to build our output logic. So the output logic, this is, for the output logic we have to figure out, is this a Mealy machine or a Moore machine? Because the output logic is different in a Mealy or a Moore. Well, this is I can tell just from this that this is a Moore machine. Why? Because the outputs are inside the state bubbles. Meaning that these outputs only depend on what state you're in. They're not affected by the inputs. If this were a Mealy machine, you would actually put the outputs on the transitions and not in the states. Okay? So in this case, I can build another truth table. Sorry, wrong one. Here we go. I could build another truth table where I look at the current state, and that's my only input. I have two inputs, so the 2 bits of current state. And the outputs, I mentioned that the traffic lights, LA and LB, are both have to be 2 bits because we have 3 different values. We have to have the green, the yellow, and the red. So you have to choose encodings for those as well. So if I am in 0, 0, that means that my LA is green, 0, 0. And my LB is red, which is 1, 0. State 1, I have an LA is going to be yellow, which is 0, 1. And LB is going to be red at 1, 0. And down here, I've got LA is red, which is 1, 0. And LB is green, which is 0, 0. And over here, I've got LA is still red, which is 1, 0, 1, 0, and LB is yellow, which is 0, 1. Thank you. Make sense? So you can fill in that table, and then you have to calculate again. You have to build a Boolean logic equation expression for each one of the, now there's 4 bits of output because I have 2 outputs, but each one of the outputs is 2 bits, so there's 4 total bits of output. Everyone with me? So LA1 is just S0. Is that true? LA1, most significant bit of LA, is equal to S1. So S1 is the most significant bit here. Oh, look at that. Yeah, LA 0, 0, 0, 0, 1, 1, 1, 1. Yeah, yeah. Looks good. And then, just 3 more bits. Any questions? OK, once you've got that, then you can build the actual circuit. So in this case, you've got a 2-bit register that's shown with a reset and a clock. Now, this is a little shorthand because we have an R for the reset input, and we have a little triangle here that represents the clock input, but these other 4 don't have labels. What are they? Well, that follows a convention where the left, everything coming in the left side is the D, and everything coming out the right side is Q. But you don't see a D or Q here, right? So when you see these schematics, you have to, they're kind of set up where the data flows from left to right, and then it loops back around from the right to the left, right? Meaning that, again, inputs are on the left, outputs are on the right of the register. Then the next state logic is shown typically on the left-hand side. So this XOR gate is calculating the next state bit 0, S prime 0, right, here. And then this guy were these 2 implicates that we put together that are joined with an OR gate that calculate the next state bit 0, S prime 0, right? Make sense? OK. And then the output logic is usually shown on the right-hand side, and that is another Boolean function, Boolean expression, Boolean circuit that uses the output, the Q output there of the register that generates the outputs, right? So this design now has all 3 components: the next state logic, the state register, and the output logic. And as I mentioned, when you design this in HDL, you would have a separate HDL block for each of these 3 components. But right for this chapter, we're just doing it as a schematic, and in a schematic, you can identify them by where they appear. Any questions about that? All right. OK, so this is where the fun part starts, because once you design something like this, you have to be able to test it and make sure it works. And this is the reason why hardware design is more difficult than software design, or at least seems to be, is because when you debug something like this, you have to be able to view the behavior of this circuit because it's sequential, and because the time has an impact here, the flow of time and how inputs change and state changes according to time. You have to view this behavior as this waveform. Now, those of you, you've all taken circuits. Do you guys use SPICE in circuits? Electrical 221, 222? You guys use SPICE?
Yes, we did.
So did you ever look at analog waveforms on a waveform viewer?
I think once or twice.
So this is similar. So if this was an analog circuit, it would be set up the same way. The x-axis would be time. The y-axis is voltage, right? Except because this is a binary circuit, the voltage is, just is discrete. It's either, 0 or 1, or it's either VDD or ground, right? But if you have signals that have multiple bits, as in the case of the traffic light color, right, or the state value, then it uses this notation where it marks transitions as an X, right? But the value is in this little, I don't know what you call this. There's like a low and there's like two lines, and the value is inside there. You guys with me? So you gotta, it gets a little, it takes a little time to get used to reading these, but what's happening here specifically is we start out at time 0 on the left-hand side, and we don't really know what's going on at time 0. Unclear what was going on. It's unclear when we started looking at this. We don't know what the initial state of this system is. So the first thing we want to do is hit this circuit with a reset pulse. So notice that the reset goes high sometime during cycle 1. It's kind of in the middle, after the first rising edge, but before the second rising edge, right about there. And once reset goes high, that causes our S prime 1 colon 0, meaning both bits of the next state, and both bits of the current state, they both go to 0. And I can tell now from looking at this that this is an asynchronous reset, because that reset caused those guys to 0 out before the next rising edge, meaning that this must have been an asynchronous reset, right? This would be a good test question. Like, can you here's a waveform. Can you tell if this is a synchronous or an asynchronous reset? This is definitely asynchronous. Otherwise, these guys would not have zeroed out until this dotted line, right? And you might say, why is there dotted lines? The dotted lines are just used as just to line things up, so you can see the correspondence between different signals. Yes.
So if it was synchronous, would it be exactly on the dotted line?
Yeah, if this was a synchronous reset, these guys would not have zeroed out until right there where my finger is, right on that dotted line, because that's when the clock edge happened, right? OK, so once you got those guys to 0, we went back to the reset state. That meant that the east-west is green and the north-south is red, just because of the way that what that state means. Light A is 0, 0, and light B is 1, 0. Why? Because that's how we encoded green and red, right? And next state and current state are both 0, because once we went into that, once the current state became 0, we had traffic on A. And, well, it doesn't matter what the traffic on B was. But because we had traffic on A, these guys are both the same. The next state and the current state are the same, which means I want to stay in that state. So as long as these guys are the same, it means stay. So do we stay? We do stay, because the first rising edge comes and we don't switch. The second rising edge comes and we don't switch. Now the third rising edge comes and we don't switch still. But right after the third rising edge, the traffic on the east-west road obviously comes to a stop at there's no more cars. There's no more traffic after that third rising edge. But notice that causes the S prime to go to state 1, which is the 0, 1 encoding. But we don't actually switch the actual state until the next rising edge. You guys with me? So this transition is ignored until, well, it's ignored until we get to the transition, which is where you actually look at the inputs and do a transition. You guys with me? Now, when that state changes, that is going to also cause an immediate update of our outputs as well. Because remember, this is a Moore machine, so if we change states, we're probably going to change our outputs at the same time, along with the state, right? You guys with me? OK, so where are we at? We're at cycle, let's see, we're at cycle 5. So cycle 5 is when we go into our yellow state for our east-west road. We're only there for one cycle. So that's why you see this guy is exactly one cycle wide. So we go to S2 unconditionally on the next rising edge. And we stay in S2 as long as we have no traffic on B. That changes at this point, but it was too late for this rising clock edge, so we have to wait till that rising clock edge, at which point we switch to state 3. We're in state, that's our yellow light, so we're only there for one cycle, and then we go back to state 0. You guys with me? So what do these arrows mean that are on here? These arrows are supposed to indicate causal relationships. So the reset has an arrow pointing to the current state going to 0, and that going to 0 causes the next state to go to 0, right? Because we switch the current state to 0, that changes the inputs to our next state logic, which then go to 0, right? Now, what would have happened, by the way, what happens if what if TA and TB were both 0 at the beginning? Well, what would happen there is we would have reset to S0, but our next state logic, our current state would have reset to S0, but our next state would have reset actually immediately would have went to S1, meaning that we would have switched from S0 to S1 right there. So we would have only been in S1 for a very short amount of time, less than a cycle. You guys with me? But the only reason we stayed in S1 for this long is because of the initial values of the inputs. Make sense? It's a little confusing when you look at it. You have to think of it like looking at. It's almost like you have to think of this as having a cursor, which is a vertical cut, and that moves from left to right. And as you cut through, you're looking at the value of each of these values, each of these signals at that point in time, at that instantaneous point in time. If you had a waveform viewer, if you were simulating this in a simulator, you would actually have a cursor that you could move across this thing to help you debug. But obviously here you just have to imagine it. You guys with me? Okay. Now I want you to point something out. I want to point something else out here too. Notice that they did something here where, for example, you have this rising edge that's going to cause the state to change. But notice that they don't. You notice that they don't change it right on the edge. They deliberately put this cross a little bit to the right of the dotted line. Why did they do that? Well, they did that because they're alluding to a little bit later in the chapter, they're going to talk about propagation delay and how we talked about propagation delay for combinational logic, but sequential logic also has a propagation delay in that after the rising edge of a clock, it takes some time for the flip-flop to update its Q output, right? So in other words, you have D come in, it gets snapshotted on the rising edge of the clock, but it's almost like you take a snapshot, but then it takes a while for that picture to come out, right? It takes some time for the Q to update, yeah. So that's why they're showing that. There's a little bit of a propagation delay between that rising edge and that. And also notice there's also, likewise, there's a difference between this cross and that cross. That represents the propagation delay of the next state logic, which is the combinational delay. You guys with me? Okay. All right, so now I mentioned that when you come up with a way to encode the states, like when you come up with these binary values for each state, I mentioned it can be whatever you want. The only restriction is the reset one should be all zeros, right? Because that's our reset. But aside from the reset state, you can assign whatever values you want. There is a trick, though, and I've never actually seen any evidence that this works. But the trick is that you're supposed to use there's different ways that you can encode the states. When I was in school, they said use gray codes, meaning that whenever you go from one state to another, you should only change one bit. So notice here I go from 0, 0 to 0, 1, I changed one bit, right? But when I went from this guy to this guy, I changed 2 bits. I went from 0, 1 to 1, 0. When I was in school, that was like, oh, you can't do that. That's bad. Well, it was bad because the presumption is that when you build the next state logic is going to be more costly if you're changing 2 bits as opposed to 1 on any one transition. Although obviously sometimes you can't avoid that depending on how densely connected your graph is. But the general rule of thumb was only change 1 bit at a time if you can. Right? I've never seen any evidence that that's true though, although I've never tried to sit down and work out different ways to do, how many gates it requires to do the next state logic for state machines that have different encodings, right? Now, people often use one-hot encoding. So instead of saying, hey, I've got 4 states, take the log base 2 of 4, that means I only need 2 bits for my state value. A lot of times, tools, synthesis tools, or in rare cases, people who actually do this by hand, instead of having 2 bits per state, why not have 4 bits per state and use one-hot encoding? Why? What's the point of that? Well, again, presumably, it allows you to have a simplified next state function, next state logic. But again, I've never seen that. But yeah, often they say the next state and the output logic is simpler when you have the one-hot encoding for the states. Obviously, I didn't use one-hot encoding, and I didn't use gray codes. Or actually the book, just did a simple assignment. Okay, well that's all the questions I have, all the material I have. Is there any questions? Anyone have any questions? Okay, we'll see you on Wednesday then.